Okay, I think it's time to start, even if I don't see our, I don't see Alison, but I guess she will join. In fact, we have quite a full agenda, so it's better not to waste too much time in the beginning. So this is the Network Coding Research Group meeting. I am Vincent Rocard, and my co-chair, Victor, will participate remotely. This is the usual notewell, so please have a look at it. And okay, those are the rules that we all follow in IETF as well as IETF research groups. So a few information, administrative information. Well, nothing special to say. You have a few links if you need. All the slides have been uploaded between yesterday and today morning, so do not hesitate. They are there, available. I see that many people, well, many, maybe not so much, but well, 8 people on the Meeteco. We will have today 2 remote presentations, one from Nicola and the other one a bit later in the program. So we will manage it. Okay, so very briefly, a quick status on active internet drafts. We have 2 internet drafts at the moment. Working group item internet drafts on taxonomy. So you saw on the list that this internet draft passed research group last call 2 months ago, and I submitted it to the next step, that is to say the IRSG last call on Monday. So hopefully in a few months, by the end of the year, it could be finalized as an RFC. And then there is also another internet draft on network coding for satellites, and that will be the subject of the first presentation, so I won't say much more. So this is the agenda. As I said, the agenda is quite full and the schedule is quite tight. So if you are a presenter, then please be careful not to take too much time. Each of us has approximately 10 minutes, and I will check that you do not extend too much beyond those 10 minutes. The agenda is split into 3 parts, 2 main parts, and the remaining one, if we have time, hopefully we will. The first part is on use cases where network coding could be or should be, or coding, end-to-end coding also could be applied. So we will go through a few situations: coding for satellite, coding for ICN, CCN, NDN, and coding for other use cases. Essentially, this idea of coding for overlay networks with the presentation from Marie-José. So this is the first part. We will have a debriefing at the end, trying to see where we want to go, what we can do, if we have the critical mass or not. So taking maybe decisions, or at least starting discussing some topics, important topics around those use cases. Then the second part will be devoted to FEC coding, essentially, with the first presentation on that will explain how to increase significantly the speed of encoding decoding operations of any FEC code, in fact. And the second presentation from myself on, well, benefits of sliding window codes for some applications. And followed by a third presentation on FEC and Quick. The idea with this presentation, FEC and Quick, is to see whether it, well, of those presentations, is to see whether it makes sense to use sliding window codes, I would say, for other use cases within other IETF protocols, not just fake frame as I did, but seeing if it makes sense for Quick, for WebRTC, for payload, or such working groups. And then finally, we'll talk about, well, a topic that was brought to the list by Frank. I haven't seen him, but at least there is Morten. So if we have time, I hope we'll, that will be the final point of the agenda. So as I said, the schedule is very tight, so be careful on that. Let's move with the first presentation. This will be a remote presentation on network coding for satellites. So Nicolas?
Can you hear me?
Yes, I can. Perfect.
So
I give you the floor.
excuse me?
You have the floor.
Okay, I'm with Emmanuel here.
Hi, everybody. We're going to speak to...
Do you have a video stream, Nicolas? Do you have the video stream? We don't see anything.
You seen it or you don't?
Yes, I see it. It is a little bit small, but we can, like, perfect. Okay, just go.
It's because we are big.
Okay, so this draft is an initiative on making a state-of-the-art of the deployment of network coding and satellite in satellite communications and opportunity for more network coding in such use case. So next slide, please. So the objective of this draft are split into 4 slides. The first of one is just that here we see satellite, typical multi-gateway satellite ground segment. It's just to introduce the vocabulary mostly. Basically, we have multiple satellite gateways covering each gateway covering a subset of satellite terminals, and the gateway is further split in 3 main blocks, which are more detailed in the following slides.
Next slide.
Next slide, please. So basically, the objective here of this state-of-the-art at that moment of that section is to identify and give the keywords that are used in the satellite industry in satellite telecommunications, and to better see where and map where it is actually deployed today. At the moment, the objective is not to go into the details of each of the words that are used here, but basically, if we look at the physical gateway, the last component, and this is where we actually do some interflow coding at the physical layer. So that is basically something deployed today, and that is part of the state-of-the-art and published in DVB standards. Next slide, please. So basically, what we want to do is to first make the state-of-the-art of where it is actually deployed, but also identify opportunities for further usage of network coding in satellite systems, basically based on real deployment of network coding schemes, but also taking feedbacks from different European projects and national projects, companies, and so on. There have been multiple and lots of initiatives in the past, and we want to have a broad view of what happened and what are the actual opportunities. So if you go to the next, basically in the next 3 slides, is a contribution that we had from the DLR, which is a network coding protocol. The scope, because the schedule is tight and we want to leave room for discussions, basically this is the contributions that we have received, and that is the kind of contribution that is very useful for this draft, because it basically describes the use case and the natural network coding protocol for using a satellite platform. And I guess you can go directly to the next slide. I don't want to go into the details of that protocol. That is not the scope of the presentation. But if you have any question, I guess that the DLR guys would be happy to comment on it. What we are looking for is a global vision and to have a synthetic view of all the activities that happened in that context. And we believe that this kind of analysis would be very useful for future architecture-oriented documents. Basically, in other words, we want to have an identification of the best way to use network coding and where we can actually put it, more than only on the physical layer, which is the case at the moment. We want the document to be quite generic. We don't want it to be, we're not looking for a taxonomy like draft, and we don't want any specific industry solutions promotions or specific architecture promotions. It's more, we have in mind the contribution to the more generic architecture document.
Next,
please. So basically, the document at the moment, we have a first section on the node of satellite topology that is basically describing the reference architecture, which I have just earlier presented, but very quickly, just mainly to give the vocabulary that is used in the satellite communication industry. and then making a state-of-the-art of what is actually deployed at the moment. And on the fourth section is to identify the opportunities for more network coding in satellite systems. And we have also a discussion on specific use case and deployability considerations. So that is the draft structure at the moment. And that is why we want to have basically we can provide lots of work and initial contribution on the two first sections, so section 2 and section 3. We also have some feedbacks from different projects, but basically if you want to contribute and to provide your contribution and to have your work identified in this and considered in this document, we are will be very welcome for section 4 and 5 mostly. And I guess you can go to the next slide. Basically, that is more an illustration of what we want to do and how we want to have a high-level view of what is actually deployed at the moment. Basically, we have the two top figures that have been taken from the taxonomy document, when we have the different layers at which the network coding can happen, and on the left side and on the right side we have more the nature of the coding, whether it is interflow, interflow, single path, multipath, end-to-end, and so on, and basically try to come up with some sort of table to have a look on where it is actually deployed. Basically, we can have upper layer source coding on the end-to-end. We also have at the moment network coding, proper network coding at the physical layer. And basically, we want to be sure about what is making the link with the taxonomy document, basically, to have an organization view of what is actually deployed. And then on the next slide, it basically we have the state of the art, and based on all the feedbacks from European Union projects, national projects, any other companies' projects, to basically identify where we can apply more network coding, mapping it with the taxonomy document. That is what we want to do. We think it's a way to visualize what is actually deployed. So basically, what is needed at the moment. Basically, what we need is to have some contributions, and particularly for section 4 and 5. We also have proposed a way of organizing the content, but we think that if you have any views on that, we would be happy to discuss, and to discuss the organization of the writing of this document. And basically, that's all, I think.
Yeah, next, last one.
And last one is...
it's a summary of what... Okay.
Okay, thank you. Is there any comment, question? I have. Okay, I have one. I do appreciate this way of making progress, because having kind of design team that will federate contributions for several people, and several people already sent to the list their intention to take part in this document writing is I think, a great thing. So thank you very much, Nicolas and Emmanuel, for taking this initiative. And I hope that we can make progress on this document rapidly, with contributions from everywhere, from everybody who's interested. I think that we already entered step 1. Yep.
Yes.
There are 2 people waiting. Yes, Marie-Josée.
So I understand that you want to limit yourself to the satellite link, right? So VSAT to VSAT, not the whole network infrastructure, because from my experience, sometimes a lot of the need for network coding may not be just over the satellite link. It could be, it's the internet, right? So this satellite link is connected to other networks, but your draft will just look at the satellite link. And
yes.
When you talk about network coding at the physical layer, do you mean physical layer network coding, or FEC at the physical layer?
What is actually deployed is the FEC at the physical layer, what is in the DFIB standards.
Yeah, because when I hear network coding at the physical layer, there's actually physical layer network coding, which is waveform coding. So I think you should be clear that network coding is at the network layer, not FEC at the physical. It's just a comment. But anyway, so I understand that now you just want to look at the satellite link. Okay, I'm good. Thanks.
But maybe a clarification. We want to look at the satellite network coding, but also taking into account the constraints that we have when you have a multi-gateway satellite. Not only the satellite channel, but also the fact that you can have some centralization of specific network functions or the specific functions that are deployed when we split the TCP connections, for example. We can also do much more things on that. So it's not only at the physical layer, but also considering higher layers, and we think that the approach that we have can be the same for other access such as cellular, for example. That's why we think it's not only specific to satellite, but also it can be considering for a more architectural document, generic.
Yes, Victor?
Yes, hi, this is Victor Fiore, BA Systems. First of all, I just want to second Vincent to thanking Nicolas Emmanuel for this initiative. This is very interesting for, I think, for me and for everybody, I believe. Just a quick question in the interest of time. Is there a particular point or element in your work that you're still looking into, you know, some research? Is there something that you're trying to figure out that would work better, or you're comparing some solutions? In other words, some the research. I'm just asking about the research aspect of this work.
So the answer is yes, because at the end of the draft, we want to provide an overview also about what we can expect in the future. One can be which solution could be deployed, and this solution can come from the experimental domain and pure research of the research domain. So okay. Yes, it is open to experimental solution. There is a section for that.
That would be great, okay, to have some kind of a lesson learned to everybody. I think that would be very valuable. Kind of, hey, comparing this worked, this didn't, this worked in this case and not in that, and so on.
Okay.
Thank you.
You could also make this more visible by having specific research direction or research challenges sections in this internet draft.
Maybe such as it is done for the network coding. In the network virtualization working group, they have a document specific to open research challenges, and we can have this kind of basically based on the feedbacks that we have, and after having summarized everything that has happened in the past, identify further areas of research. Yes, we can add a section to that.
That would be great also.
Okay.
Good point. Thank you. Anything else? Any other comments? No? Nobody's waiting in this? I'm waiting too? Okay. So thank you very much. And let's switch to the second topic. So second topic is on network coding for ICN, CCN, all those information content-centric networks, and which is also one of the main fields where network coding can make sense. So we have two presentations, one from Cedric and one from Mitoshi. So Cedric, if you want to come. Yes, Pingbox.
Stay between the lines.
Hello.
Does it work? Is it on?
It was working a few minutes. Well,
I think it is. Okay. Yeah. So, well, thanks for inviting me to participate in this. So at first, the original, I think on the wiki, I don't know if it has modified, but it was talking about some paper that we wrote about network coding and ICN using combination of those two things to do video delivery. And then after talking a little bit, Okay. After talking a little bit with Vincent and people, I thought I was going to do a more of a like kind of description of what CCN is and kind of describe it a little because it might be necessary to provide a little background. So how do I change the slides? You do it for me?
You tell me.
Okay. So there's a ICN research group in the IETF as well that met, that had an interim meeting on Sunday and a meeting yesterday. And one of the RFCs it produced, RFC 7933, has like this kind of paragraph on network coding. And so that started, I mean, it was inserted in there because it's kind of a placeholder for a conversation for network coding and ICN in that discussion. And I guess later we can talk about how those two research groups could synchronize on this. And then there's some papers on the topic that we did. I think we did the first one with Marie-José and Dirk Trossen in 2012. And then there's some other papers. And this kind of those papers at the bottom are the one I'm going to talk about today. So the Netcode CCN from University of Bern. I'm not a co-author of that, but they kind of they ran away with the idea of this first paper. And then in return, we took their code and we did this implementation of the adaptive video streaming on top of Netcode CCN and kind of solved some of the implementation issues to do that. Okay, so so I wanted to started with a little background on ICN, and ICN here in this context is going to be CCN. CCN stands for Content-Centric Networking, has been proposed, I think, in 2006, 2007 by Van Jacobsen when he was at PARC, and has been one of the NSF funded for future internet architectures and CCN/NDN. NDN was the name of CCN for that NSF funding project. NDN stands for Name Data Networks. So that has been around for a while. And the key principle of it's that you have different semantics of IP because everything is a request-response exchange. So and for that handshakes, you have two types of messages. You have interest messages and data messages. So you have two types of packets. And the interest carry the name, and the packet format is on this picture, and contain also some options and some parameters. And then the data packet returns the content name as well and some signature information, security information, and then the payload as a data. So the way the network is architectured is that so the client who wants to receive some data is going to send an interest with that name, and that interest is going to be received at an ICN router, and that router is going to have a couple structures, data structures in the router, and those data structures, there's a content store, and which basically is a cache. And then there's another table which is the pending interest table. So that's a list of the interests that have been received and that are waiting for the data. And so in the data structure that I mentioned before, in the packet format, the interest had a name, didn't have a source. It didn't say where the source was. So that's kind of the intent here is to provide some level of privacy. However, because there's no indication of the source of the packet, then you have to create a state in the router to route the data back to whoever was requesting it. So that's what that pending interest table does. It's the state, it's a transient state that says, well, I received the request for this data from that interface. So when I receive that data, I have to forward it on this interface. And then you have the fib, which is going to tell you when you receive the interest, you're going to look up at the name, and then on that name, you're going to do some matching in that fib, and then you have some divergences between different protocols. Some do an exact match, some do a longest prefix match, but on the fib, you're going to do on the fib, you're going to do a prefix match to find where you're going to forward that interest based upon the name. I think that's what I'm, yeah, so basically when you receive the interest, what's happening is there's a lookup to say, well, for the name, is that data that is being requested in my cache? So you first do a lookup on the content store. And if that's negative, the data is not here. If the data is here, you return the data and you're done. If it's not there, then you add to your pending interest table a state saying that I've received a request from that interface. So for instance, in this case, I've received that request for that prefix from that interface 0. And then you're going to look at up the name and forward according to wherever interface is matching. Let's go next. So one of the thing is the interest that can be sent also over multiple interfaces, and one of the advantage of CCN is you request chunks, and there's no session that you have to establish for this. You just send an interest for the name. You don't have to create first some kind of session. So you can use any interface that's available to you. So if you're on a wireless device, you can use LTE and you can use Wi-Fi or whatever, and you can send interest on all these interfaces. But if you want to send, if for instance, in this case here, you have a very simple example. That's the example from that paper from 2012. Where the client is going to send some kind of interest, and then the router might decide to send that interest onto 2 different servers because it's not sure which one, because for that prefix it has 2 routes that are listed. So in this case, if the servers return the data, then two servers the 2 servers might return the data. Is that the case? One of those data is just going to be discarded, and the other one is going to be returned to the client. The idea of applying network coding here is it's very straightforward. You just say, well, if you request for a network coded segment instead of just the first segment that you want to get, then those 2 servers might return different linear combinations. So you're still gonna discard one in this case, because there's this balance of saying 1 interest and receiving 1 data. You cannot receive 2 data packets for 1 interest. But at least the 2 things that you're gonna keep at the 2 packets you're gonna receive at the router in the middle are gonna be different, and you can decode them, and you can have the original packet in there if you wanted to. And once the client is going to send the request for the second one, it's not going to go all the way to the server. It's just going to go to this router in the middle. So so let's go to the next slide. So the benefits, of course, is to combine the benefits of ICN, which is of this sessionless transport that connect directly to the content. That supports some kind of mobility in a more graceful way than having to set up some kind of session, that has this native multicasting, and that kind of take advantage of this ubiquitous caching. So that's kind of the benefits of ICN. But you add to this the benefits of network coding, which is this kind of asynchronous use of multiple interfaces, that if you multicast an interest to multiple sources, then whatever data is returned to you is not lost, but can be cached closer to the person to the client who made the request. And you can populate the cache faster if you have multiple clients requesting the same data. So you have different scenarios. You can look at unicast scenarios or point to multiple point scenarios where in every case there's some benefit of the network coding, and then of course you try to preserve the 1 interest 1 data flow balance of CCN. So what happened then? There's this netcode CCN paper that was presented at Infocom last year by a team from University of Bern, and they kind of implemented it and wrote out some kind of specification. Our original paper was more of a position paper. And so now you can request a coded segment, and you don't have to specify a specific segment ID. You specify that you want a coded segment. So you have some kind of way of indicating this in the naming. The name carries kind of that you request. Well, there's a bit that tells you, I allow for network coding, and in the name that is returned to you, you have embedded the coding vector as well as the generation of the video. So if you have a specific file, you're going to cut it in different generations. Each segment within the generations are going to be encoded together, and you do this so you don't have to wait until the end of the file to decode everything. And then you have to modify the procedure at the router, of course, of the interest and at the how you handle the data as well. And it's discussed in the paper. And I don't want to get into the details of it, but if you're interested, you can look at the papers. Next slide. So, but the key difference, and that's a picture from that paper, is that the interests are not filtered out in the same manner. So, for instance, with the typical CCN, if you have interests that are received, in this case, you have 4 interests are being received on 3 interfaces. So the first interest is received on interface A, and actually one of the idiosyncrasies of CCN is that they rename stuff. So like instead of cache, they call it content store. Instead of interface, they call it face. But which, you know, it's a little Orwellian if you ask me. But anyway, so the first one, the first interest is received on interface A and is being propagated. Both the top case is regular CCN, the bottom case is the coded CCN. So in both cases, it's the same. Then you receive a new interest, and now it's on a new interface. Second interface arrives interface B. This one is not propagated because you already have one that's outstanding interest, and the data that's going to come back is going to be responding to both those interests, right? The third one comes on interface C. So then again, you're not going to forward that interest because the data that's going to come back also is going to satisfy this one. But then the fourth one, in the case of regular CCN, it's also being ignored because it's just a duplicate of the previous one. There's no action taken that. I mean, for the second and the third one, you put an entry in your PIT saying, you know, when I receive the data, I send it back to interface B and to interface C. But the fourth one, you do nothing in the case of the red arrow. However, with the coded CCN, you forward it because now it becomes something that requests new degrees of freedom. So, oops. I'm gone.
You're a bit long.
Let's go to the next slide. Anyway, so we took that code, we merged it with like a Dash implementation, and we demonstrated some benefits of this, and particularly seamless mobility. And the way, so part of the implementation, what we show is that if you add more interfaces and you send the interest on those interfaces, then the rate adaptation can view the whole link between you and those multiple servers as one logical link to the copy of the content and perform rate adaptation on that logical link. So that's kind of a cool thing to have. And because you use network coding, you don't have, technically you could connect to different servers, have different link to those different servers and make different requests for different packets on those different servers. But you have to be cautious because you would have to make sure you don't request the same thing on the different links, and you would have to make sure you request them at the right rate on the difference link. In this case, in our implementation, you don't do any of that. You just do the control. The rate adaptation logic is that of Dash and is not modified, and everything underneath is transparent. And because, you know, network coding is inherently asynchronous, you can just, you don't have to worry about anything. So there is some little, okay, that's a hint to move on. Anyway, that's it for my talk. You know, thanks for hearing me. As far as what the next steps are, there has been some interest on this domain. I was actually surprised by how much there has been over the last years on that paper we wrote a couple of years back. And so definitely there is some kind of people, and there's another presentation on the same topic coming up, and so that's good. But you know, and if this research group would like to take on this work, I think that's a great idea. But you know, just kind of offer it, you know, to you guys as well. And also, I'm more involved in the ICNRG group than in the NWCRG. But you know, so it would be nice if there's well also to build bridge with that other community. Anyway, so you have questions or you have remarks or comments?
Yeah. Thank you, Cedric. I think we will take questions at the end, because now there is the second presentation on the same topic. So we will talk about those future steps at that time, if you don't mind.
Well, so if question on this specific topic, no, we're all good. Great.
No, it was clear. Thank you very much. Hitoshi? Just wait. So same topic, second presentation.
Okay, so I'm Hitoshi Asaida from NICT, and this work with my colleagues Kazuhisa and Cherry Tourette in India. And this paper was accepted in Infocom, so it's already presented in last Infocom conference held in Atlanta. So the title is Low Latency, Low Loss Streaming Using Network Coding and Caching. Next, please. So the motivation of this work is to fulfill the various requirements, especially for the target, which is a UHD level 4K or 8K delay-sensitive video streaming. Delay-sensitive means real-time streaming. So the requirements we formulated were low latency, about 150, for example, 150 milliseconds for interactive communication. This 150 milliseconds is defined in the ITUT recommendation. And we definitely need to have a chance of the low packet loss to maintain high QoE. And of course, from the network perspective, efficient packet delivery to support a large number of receivers, because high quality or high bandwidth streaming, if the large number of receivers receiving the same content, then the network will be consumed. So the proposal is L4C2, low latency, low loss streaming using network coding and caching. So what is L4C? The basic idea is that we leverage CCN NDN features. And because a CCN NDN can leverage the name-based data request and forwarding and natively support multicast and multipass. And we enable adaptive hop-by-hop data forwarding within an acceptable end-to-end delay. Acceptable end-to-end delay is, let's say, it's 150 milliseconds. And the hop-by-hop data forwarding is something like a fashion of the CCN and NDN. So it's natively supported hop-by-hop data forwarding. And so to fulfill this requirement, we use network coding, which is actually random linear network coding, RLNC, and also in network caching. It's natively supported by CCN and NDN for efficient data recovery. And also data recovery within an estimated acceptable link delay. This acceptable link delay is not an end-to-end delay. End-to-end delay is a requirement for the application. Acceptable link delay is something like a requirement for the calculation of the retransmission for the lost packets. And the data recovery based on the measured data loss rate. And to support these functions, we newly defined the symbolic interest and the control interest. Because the CCN NDN, for the simplified reason, so for the simplification the reason, the regular, we call it regular interest. Interest must be sent to get the data, as Cedric mentioned. But that regular interest may cause some problematic situations I'll explain later. So we newly defined SMI and CNI. And SMI used for streaming requests, including layer information, and the control interest is used for RTT measurement, notify redundancy level for encoding and switching to regular interest. So this is a system architecture. We make something like a separation for control plane and data plane. For the control plane, the user, consumer, send an interest, different kinds of interest. Symbolic interest, regular interest, which is defined by this predefined CCN and NDN, and control interest. For the data plane, you can see the one video source, and you have a large number of consumers receiving the same content. And the video source can be layered, and the layered encoding data, and also the redundant coded data is transmitted from the source. And the intermediate routers can cache the content itself and also the coded data as well. So the receiver, briefly I explained the situation. So the receiver when he receives the content and he detects some missing packet, then he may request the retransmission of the missing data. But if luckily you have the missing data is cached in the network, then the content can be transmitted from the cache. But unluckily, if you don't have the cached data, but luckily you have the coded data, then you may create the coded data inside the network, and finally you retrieve the complete packet. So the network coding is applied for each coding group, which consists of the k different original coded data packets. Encoding vectors are randomly selected from Galois field to powered by A, and k is set to a constant value considering the waiting time to recover lost data. So this is one of the core functions for estimating link conditions. The data loss rate can be easily calculated because we detect the sequence number and the network coding parameters stated in the data header. So the receiver can easily calculate or recognize the data loss rate. And but acceptable link delay, it's something like hop by hop delay. This is a little bit difficult to measure the hop by hop delay. But basically, the application itself is transmitted within 150 milliseconds. This is our assumption. But if you receive the data, so let's assume that the source already encoded absolute time. Sorry, absolute time. So he can recognize, okay, so this content coming from a source with several period, let's say 100 milliseconds or 50 milliseconds. So he has something like a still budget. If he received the content from the source and he calculated this takes 100 milliseconds, then you have a 50 millisecond budget. And so that within the router, if this 50 millisecond budget can be used to encode and decode the lost data, then you can use this 50 millisecond. This is what we call the timing delay budget. So each router calculate and measured the RTT between them, and this to make this kind of measurement, we define the control interest. This control interest can measure just a response like a ping. So each router has such kind of information, and if you receive this CNI, for example, router I now just send a CNI to router J, then router J respond with the link delay between source and J. So he can recognize, okay, so from J to S, the delay must be, let's say, DSJ. And the router I also informed if he received the CNI from downstream, then he can send the total delay from source to router I to his downstream neighbors. Then each router has the knowledge about the budget. So I don't explain the very detail today because of because it takes time. So we directly now explain our simulation results. So this is a simulation we set up, and this is done by NDN Sim. And we have a real-time video rate, total 35 megabps, and this can be reduced with the reduction of the layers, so 20, 10, and 5 megabps. And the interest data and the data packet size is 100 or 1024 bytes. And the acceptable end-to-end delay is 150 milliseconds. And the scenario is to investigate user QoE using an existing QoE model, and the comparison with state-of-the-art for multiple data retrieval in CCN, which is proposed in previous ICNP. Go to next. So this is a result. So the green one is this paper, and the red one is our L4C2. And maybe it's better to see. So thanks to the mixture of CNI or regular interest and symbolic interest, we can strongly reduce the number of transmitted interest traffic, something like a signal, because CCN or NDN just requires exact match for the received contents. So if we use something like a symbolic interest, then we can omit the bursty or high rate interest transmission. So we can hardly reduce such kind of signal. And the left side figure shows that we increased the normalized QoE comparing with the last ICNP paper. So that's all for our paper's explanation. So this slide just shows, this is something like my personal opinion that I already sent to the mailing list. And so we may be able to contribute to various work in this network coding research group. For example, potential work in network coding research group. I don't know, all of you or many of you can agree to this thought, but I think that, for example, describing a common research challenge is interesting. So what kind of research should be done for network coding, in network coding, end-to-end network coding, end-to-end efficiency, and so on. And also, we can have a chance to describe a baseline scenarios, especially, for example, for network coding for ICN, CCN. As Cedric said, we have various maybe research work for this area and this domain. And then we can maybe discuss about in-network coding, including the clarify the problems statement and introduce recent work, compare with RNC and other codes, investigate block coding versus sliding window coding approach. By the way, our approach is just based on the block coding because of the simplicity. So our future work is related to the adaptation of the sliding window coding approach inside our proposal. Okay, that's all.
Okay, thank you. Thank you for your presentation. So I see that it quickly goes into very specific details with all those interests specific to your work. So it's very technical very quickly. So, but anyway, thanks a lot for this presentation. So let's talk a little bit about this topic, network coding and ICN. So first of all, I would like to say that Thomas Nikolaos sent me an email. So he sent an email to the list explaining that there was this paper that Cedric mentioned about netcode CCN available. And he sent me an email just to tell me that, okay, he couldn't join today afternoon, but he volunteers to take part into this activity and to contribute. So that's the first point. So next point is that, okay, I think it would make sense since there are at least 3 people interested and probably a bit more, we'll see, into this topic. It would be perhaps interesting to have the same approach as we had previously for the previous topic, satellite communications. That is to say, trying to set up a small design team, a few people interested and volunteer to contribute and work jointly. So I hope that you all would like and agree to work jointly on this topic. Well, that's the first question to you and
Sure.
to you, Cedric.
Sure.
Sure. Perfect. So that's a good point. And then, well, try to organize the ideas, organize the domain into some outline and filling this internet draft outline progressively. That could be a way to move forward. Yes, Alison?
So this is Alison Menken, IETF chair. I wonder if you're going to have some design teams, whether you might want to create a kind of a template for what is in a document that takes a certain aspect of FEC and then put some consistency across the documents, because there's probably there's quite a bit of common ground in terms of describing why you're doing this and what are the kind of components.
Yeah, this is a good point. Yeah, we can try. Good. So there is this generic part in this internet draft that will be the same more or less for all design teams subjects, and then the specific part to the specific use case. Yeah, we can try to do something like that. Yes, good point.
For example, for the common research challenge, this doesn't mean we only concentrate, for example, network coding for ICN or CCN. So, for example, this is my personal opinion, but there are several common research challenges, including ICN, CCN, satellite, wireless, and other stuff. So there are a lot of architecture, or there are a lot of various or different link layers or different applications. So the research challenge could be different, but we can summarize. For example, for this domain, we should address this kind of issue. For this domain or for this kind of network condition, then we should address this kind. So the research challenge itself can be, as for example, this is my personal opinion, but can be something like a single document. But for the baseline scenario, it's a little bit difficult to concentrate only for the one general solution or baseline scenario that can be adapted to various network or various applications. So the baseline scenario, for example, we can form some design team, let's say design team for ICN and the design team for satellite, I don't know. But so this is something like my personal opinion.
Cedric, do you want to add something? No? It's okay. Okay, perfect. Yeah. I hope that there will be other people interested as well. Oh, Cedric, yeah.
So Cedric Adjé in RIA, I just want to say that I think this topic very interesting, and I will just want to mention that I could participate in any document. Yeah.
Okay, perfect. There are many situations where it can make sense to have this kind of architecture of solution for distributing content. On the list a few months, 1 month ago, maybe we mentioned the possibility of having this approach for distributing content within trains, for instance. So yeah, I think a good potential behind it. That's great. Okay, thank you very much to both of you. Let's switch to the next presentation. First, I don't know if new people came and didn't sign the blue sheets, which is the case. That's the one. Thank you. Okay, so let's switch to the next topic. So other network coding potential use cases. Well, in the agenda, there is this presentation from Rolf. So I see that Rolf is online on Meetecho. Unfortunately, and I need to apologize, I was not very clear and not clear enough with Rolf on what was expected for today afternoon. And in particular, I was not very clear in the fact that we were looking for existing solutions, more or less, on different domains for applying network coding and coding. And therefore, what he sent me was more on potential use cases where it could make sense to have coding, I would say, instead of having a presentation on existing solutions. So I don't see if you see what I mean, but I will not go into the details of this presentation. I will just briefly mention what was inside. For instance, the fact that, okay, we have some slides, some content about high density sensor networks, let's say that this way, either for CERN particle collider experimental infrastructure, where you have many thousands of sensors at the same place, producing a very huge amount of data in a very short time frame, and where it could make sense to have some kind of coding. But for the moment, we don't know if it is the case or not. So that's one potential use case that he identified. Also, this use case where you have containers, each of them equipped with sensors that will produce regularly some data, and where it could make sense to have coding. Then those two use cases related to vehicles, either trains or cars, that will communicate with one another, and where also it could make sense to have network coding. I'm sorry, but I go through them very rapidly, as I said. And finally, this domain where you have coding for content storage, NAS or SAN or cloud storage. Okay. So, but I don't want to enter into the details because I said the slides are not very well focused on what I had in mind. So I apologize, Rolf. I don't know if you want to add a few words, but I want to apologize with you. I was not very clear on what I asked you. So anyway, this is work in progress. If you know that in some specific domains that were mentioned here, you are aware of network coding applications, network coding experiments, if you have feedbacks, then please tell us, and we will try to go further into details next time. Rolf, anything to say? No? He told me that his network connection would not be very good, so I don't know if he can participate. Anyway, so let's switch, and if you want to say something, Rolf, you can come back later on. Okay, let's switch to the next presentation from Marie-Josée. This is a joint presentation with Brandon Williams from Akamai on something that we mentioned on the list, this generic, robust, low latency tunneling system. Thank you. You have the floor.
Oh, hi, everybody. I hope you hear me. Thank you for allowing me to present. I'm sorry I couldn't be there, and I think Brandon also apologizes because he couldn't be there. So this is very recent work that we started doing, I would say the early part of that maybe last year and going all the way yesterday afternoon. And there is part of it which has use cases that relate a little bit to what Vincent just presented, and also to the presentation on ICN CCN. But this is actually looking at it from a more, not network coding as a set of libraries to do coding, but how do we introduce network coding as an element in a toolkit to enhance performance in a network? So I know I don't have the slides, I cannot move the slides, so could you please get to the next slide? So there is some new use cases. I think we've heard about on the list about NFV. We learned about SDN. And a lot of the work, if you look historically, I think Cedric to have mentioned our paper of 2012, in past 10 years actually, the main focus of the FEC at the network layer have been very much for wireless and streaming video with performance and combined with performance enhancing proxies, proxy-based forward error correction, but mainly for the wireless and streaming. But there's a lot of other use cases that are on the rise. Obviously, all the enterprise work that's being done on overlay networks. The cloud computing, a lot of people understand the computing part of the cloud computing, but don't really get that there's a cloud and you have to get in and out of the cloud and keep performances there. And I would say from the previous slide, a previous presentation, there was this thing about the mobile fixed network, the airplane, the peer-to-peer, the multi-satellite, the trains. And this has some kind of a rebirth of this, I think, in terms of some kind of an of the internet. So what we feel is that what is needed is some research and implementation of some flexible, dynamic application and policy-based mechanism. Because we need to enhance the performance of these rising services beyond the traditional quality of service, which was essentially just prioritizing services and allowing them to have enough bandwidth. Next slide. So what we suggest is to look at some kind of a robust, low latency tunnel. And what do we mean by that? And we would like to have a dynamic negotiation performance inside the tunnel. When the tunnel is established, instead of just being de facto, I'm going to send all my stuff there, what is the performance that this tunnel is going to give us? And should we use this one or another one? Should we use some FEC or not? Should we use all kinds of other performance enhancement through that tunnel? And I'm going to come back to this in the next slide. And to essentially define my end-to-end semantics from where I am at my application going to where I want to go and the other applications. We want it to be completely in user space. We don't want to be impacting things that are below us. There's a lot of issues now with middle boxes being introduced everywhere on the network. And I'm sure that you guys, some of you went to the TLS meetings where there is issues with middle boxes. We don't want it to interact with crypto. We don't know where the VPNs are, and we don't want to deal with that either. And we do not want to have network termination hop by hop if we don't have to do it, because it's so complicated to restart everything and redefine what is needed at the next hop. Next slide. So what needs to be negotiated? Well, we're inside this network coding research group, so obviously that's the use of the FEC algorithm and the implementation we want to use. And those depend not only on technical issues. Do I have, what is my error rate? Is it bursty? Is not bursty? But there's also legal constraints and requirements. There's patents in this field. There's software licensing. Do I have the right legal rights to use this? As my destination have the right to use this? So I think we want to be able to negotiate that. Obviously, there's this reliability requirements, which is central. So based on packet error rates and profiles, I think it's not just the error rate, but also the burstiness. When we look at things that come from the physical layer, it has a tendency to be a little bit more random because of the other implementation of FEC at lower layers. But when you start looking at the network layer, there's actually a lot of burstiness and very long burstiness, and your code has to be able to adapt to this. Do we need in-order delivery? For some applications, yes. For some applications, no. And it actually relates this time to maybe the difference between having video versus page load, for example. Do we want to have, basically, to trade delay tolerance with reliability? If we can't tolerate delay, maybe we can have a more reliable system. This has been essentially the main goal of forward error correction for about 70 years. Would we like to have packet pacing to maintain constant delivery rates? That actually helps also in the monitoring of the network. I'm sorry. Congestion control and fairness. Actually, this is a question. For example, do we need the protocols to be TCP aware? There is some network coding work that's been done that is TCP aware. There's some that is done that is not. And a big one for us is this microflow support versus muxing. And we would like to have the microflow to be independent from the tunnel protocol evolution. So if the tunnel itself evolves, our flows that are within it should be untouched by it. Obviously, some of these are implementations, some of them are still research, and I think the whole set of this is actually a nice network research project. Next. So actually what exists and can be built upon, but obviously there's a growing number of FSC codes and protocols. The quick tunnel, it's not the quick tunnel codes, but the quick tunnel code. And I think Ian Sweat, who presents later, is going to talk about this. There's from TAPS, there's concept to decouple application from transport, which relates a lot to this. There's some new path-aware networking research that has been proposed in this IETF, and there's other, and also related to congestion control, the SDN, but also relating to what Cedric presented. We gave some thought to how this this implementation or this way of thinking of things could actually be embedded into an ICN and CCN framework. And actually, if you think of publish response or data response or query response, there's actually a way to do the same thing, because again, there is a negotiation. Next. So we feel that there's next steps to do this. There's been a lot of talk again on the list about architecture. There's many ways of looking at architecture. I think in this case, it's more like a network architecture draft. And I think based on the numerous implementation of network coding inside networks, they could be an implementation draft on how to do this within what is existing. And we would like to know if this is important work for the future of network coding as part of the network coding performance toolkit. We feel it's important, but again, it's, we're suggesting that to the group because it's a bit out of the current scope. Next. And again, so I made this very generic because it's a very recent idea, but I would like to thank Vincent and Ian for some of the talks that led to this, and of course, the people at Akamai who have helped into some development that helped us focus our ideas in this. So that's about it.
Okay, thank you, Marie-José. I have a technical question, and then we can continue with this with those questions about what to do next. Technical question is about the use of potential use of in-network recording feature. Do you believe that it will be that this tunnel will use only end-to-end coding, or also it is necessary to have recording within the network? Do you have an idea about it?
Well,
or not yet?
Actually, not yet.
Okay.
But I think that in the idea of the microflow being independent, it actually doesn't prevent this microflow to be re-encoded at one point. And again, I think for the moment we looked at end-to-end semantics, but I think we could think about it also in what happens if there could be, I think there could be some in-network, but we haven't really thought about it yet.
Okay, and this idea of microflow, I don't really understand what you mean by.
Okay, so okay, what we think is, do we want our tunnel to be destination-based, where we mux everything into it, or do we want the tunnel also to be aware of what are the specific sessions that are within it? So the microflow is the specific session versus the whole mux thing. Okay, I understand now. Okay, thank you. Okay, so there are many important research topics in this potential activity. Very interesting questions. So the key question, I think, is whether there is a critical mass to address this topic as well, in addition to the previous two ones, or not. That's one of the key points. But I see that there is support, and strong support, I would say, from Akamai. I guess. And I think it's a good implementation. Well. It's a potential good implementation to be included with Quick, but I will let Ian talk about that.
Okay, so potentially also with Quick, good. And these among people who are present today afternoon, are there anybody interested? Is anybody interested as well on this topic? I am, as far without my chair hat, but I am also interested, but. Who else? We'll go to the list anyway, so you can think about it and answer later on if you prefer. I see nobody. Maybe Victor? Victor, you have the floor.
Thank you, Marie. This is interesting. Just a quick question. I think it has potential and interest in the group. We'll see on the mailing list as well. Something interesting that I saw on your brief presentation is that the end-to-end, the application level component, the part where you express the various performance or otherwise QoE requirements. That's clearly something that we did not, as you said, it's a little bit out of what we initially thought in the charter and so on, but I don't think that would be bad to actually have as a research topic. In other words, in short, I think it's interesting, and we haven't actually discussed or considered this topic yet. So,
I think as the applications become much more varied, I think there's going to be a lot of these things that's going to pop up.
Yeah.
If you remember when we started, it was very different.
Yes, I agree. I think this is interesting. We haven't discussed that. Clearly, it has implications. Whatever the application wants to do or wants from the from the network service that would be made possible by this tunnel that has the network coding and other other machinery under the hood. That would be interesting, and the implication of what out of what the application requests, because application normally is agnostic about what is it, a network coding, is it some other mechanism under the hood. It is important that at that point of inflection at the interface between application and the network is what are the implications between the requests and mechanisms that can provide that kind of service. So I think that's good, interesting. Thank you.
Thank you.
Yes, Nicolas? We cannot hear you, Emmanuel. No, still no sound. No, we cannot. Sorry.
Well, you can send the question to the mailing list. I'll respond.
Yeah.
Is it okay now?
Oh, yeah, okay.
It's okay. Let's go.
No. Okay. So it's a question from both. Finally, it's not only me, it's me and Nicolas. The question is, it sounds like more a problem of traffic engineering than a problem of network coding. And I don't see, you presented several solutions, but it was much more related about network engineering, network traffic engineering, rather than network coding itself. So,
okay, I agree with you. And that's what I said. It's actually to put network coding inside a toolkit for traffic engineering, if you want to put it this way, or network coding inside a toolkit of, I would say more network engineering. I agree with you. This is not network coding research, and I actually said that this is not looking at codes. This is looking at codes inside an infrastructure for traffic engineering, which I think is networking research, maybe more than network coding research. But I think because it implies the use of network codes in maybe different use cases and everything, I think it is related to this group. But I agree with you. This work will not lead to new network codes. It could lead to new, maybe encoding and decoding requirements that could be sent back to the coding people. But yes, I completely agree with you. This is not network coding research. This is network research.
So maybe that's where there's a link also with when we wanted to speak in our draft on the deployment of network coding techniques in satellite system. For example, we have the question on the interaction with virtualized work, and basically, I don't know if we speak about lots of subset of functions that need to be interconnected, maybe it's more interesting to try to target more working groups such as the service function chaining working group or network function virtualization working group, where basically they have use cases on deployment.
Because there are other groups working on tunneling and stuff like that, and I think we have to see what they are doing before.
Well, I think that's part of the work. I'm not saying that this is, none of these things is independent on its own. But any case, I think if the group thinks this is not interesting, I don't mind. I think I don't know. I'll ask Brendan to support this remark. But if this is not interesting for network research, we can actually take it to transport.
Maybe we can give the floor to Brandon, who's waiting. Nicolas, if you don't have anything else to add.
Yeah.
Okay.
Yep.
So, Brandon, we are listening to you.
Okay, can you hear me?
Yep.
The point I wanted to make about the network engineering aspects is that I think what we're really focused on are the ways in which application of the codes at the network level actually directly impacts the network engineering. There tend to be a lot of tunable parameters related to how the codes are applied that have a direct impact on the network quality and the quality of experience for the application. The tunings that are appropriate for real-time video will tend to be different than the tunings that are appropriate for data transfer and that sort of thing. And the idea is that for really effective application of network coding, we somehow have to take into account the impact that it has on the network engineering and sort of the interrelationship between the tunable parameters for the network codes themselves and the quality of the network experience. That's really the focus here, not so much on network engineering overall via protocol, but rather negotiation around the aspects of the codes themselves that have an impact on the network engineering.
Okay, thank you. Nicolas, you? No, I think he has no question anymore. We are 2 minutes late.
Yes.
This is okay. Okay, yeah. We'll listen to you if you want to add something quickly.
Yes, it's just that it is much clearer now, and we understand the need for the
at the application level.
The application level.
Yeah,
I think
on QoE experience, not on the network. That's why we were a bit confused.
That's now the link with the TAPS working group is clearer in the slides, and also that's why we understand better in the problem with our interface between what you have, the network coding solutions that you have, and what is actually deployed at the moment at the application level, and we could do more. And that's also the link with the quick presentation that will come after it's clearer now. Thank you.
Okay, thanks.
Okay, thank you. Anyway, we will continue on the list. I think we need to make progress and switch to the next presentation now. So thank you to everybody for your contributions.
So, hello. So my name is Jonathan Etchard. So I will talk about coding technique to improve the speed of eraser codes. So note that some parts of this work have been patented. So next slide. So before giving you some details, I will give you the use case and the context of this coding technique. So next slide. So just a brief reminder. So suppose you want to send some packets over a network to another node. So you want to protect them by adding some extra packets. So you generate some linear combinations. You send all these packets, and if you have losses, you reverse the operations to rebuild your missing source packets. So that's why we need to use the finite fields to perform these linear combinations. So if you're interested, Planck wrote a really good technical report about finite field arithmetics applied to eraser code. So it's a good entry point if you are interested. So next slide. So now the problem with finite field arithmetic is the operations are complex. So the solution is to move away from this structure to go into another structure called a ring, where operations like multiplication are much easier. So it's fast. So we use fast transforms to move all our field elements into a ring element, a bigger ring. We perform the multiplications inside this ring structure, and then once we get the results, we go back from this ring to the field. So it's a known technique based on ring decomposition, so it's not new. What we did actually is the definition of new transforms. So next slide. For the ring transforms, so basically you have these operations to do. So the vector represents your data. So you have thousands of bytes of data. So that's your packets. And you have a matrix. So the first thing you need to do is to transform your data. So this transform must be fast because you have a lot of data. So next transform, next slide, is about the generator matrix. So this transform doesn't have to be fast because that's few elements, but the elements you get must be well chosen. And when we move from the field to the ring, actually we move into a bigger ring. So we have a choice to do. So that means one field can have several representation in this ring. And by using this, we could reduce the complexity. I will explain later. Next slide. So you perform the multiplication in this ring. Okay, so you get ring element. And now we apply the reverse transform to go back from ring elements into field elements. Next slide. Okay, so the first transform you could use is called the embedding transform. So it was described by Ito in 1989. Okay, so it's very fast to transform finite field elements into ring elements and back. And additionally, we added two other transforms. So the first is called parity transform. So like embedding transform, it's very fast to transform finite field elements into ring elements and back. And the most important is the sparse transform. So this is the transform applied to the matrix. So it's very efficient to reduce the complexity because it will choose the good element into inside the ring. So next slide. I don't want to give you some details. If you want to do some details about these transforms, you could read this paper. So we presented. So here is the final scheme. So you applied a special transform to your vector data, and you applied another transform to the generator matrix. So just to give you an idea of how the sparse transform can reduce the complexity, let me give you an example. So next slide. When you have a generator matrix, it is composed by field elements. So a well-known technique is to convert this matrix into binary matrix where each entries represent a XOR of a part of a symbol. So on the left matrix, you have this unstructured matrix. It represents all the XOR you need to perform the operations inside the field. Now, if you move from this field to a ring, you get the right matrix, okay? So the first thing you see is you have less XORs, so less entries, so you have less operations to do. And then if you look well, the 12 elements are composed by cyclic diagonals. So that's an important thing to optimize the coding operation. So, okay, that's all. So now we implemented our method and compared our codec to the fastest implementation we know. It's called ISA-L. It's developed by Intel. It's open source, and it's a fully assembly library. Operations, so it works on Intel, ARM, anything you want. It allows also the use of uncommon fields like the GF64 because it's not possible using other techniques like lookup tables with this field. And this field is very fast and also provides good capacity correction. So we tested inside our Tetris code, and it has good performances. So it's cool. And I'm done. If you have questions.
Thank you, Jonathan. Well, it's great because you could have made a very complex presentation with a lot of math.
It's tricky to talk about that, yes.
And the result is, in fact, quite easily understandable, and we really get the points. That's great.
Okay,
thank you for that. Yeah.
Yes, Cedric Adji in RIA. Just a basic question. You go from a field to a ring, do an operation, and then you go back to the field?
Yes.
So the point is to just to be faster, and the operation is isomorphic?
Yes, yes. So not all operations are isomorphic, that are homomorphic most of the time. Yes, and that's the goal, yes.
And why you don't stay in
the ring?
Yes.
Because when you transform the data from a field into a ring, you have bigger data, actually. Because your ring is bigger, so you have to represent it with more data. That's why you need to go back. And actually, the transform just adds some redundant. So the parity transform is just a XOR of all your monoms of your field elements.
Okay.
That's why you need to go back. Thank you.
Morten Petersen. So I think very interesting stuff. One question I had was this transform, is that included in these benchmarks, or is that, so do you do the transform, then the operations?
It is included. It is included, yes, of course, yes.
And the transform, is that also an XOR, or you say it expands the elements a little bit?
Yeah,
so if I have a gigabyte file, what would be my...
Yeah, actually, can you go back to the transform slides? The previous when I described, yes. So the embedding transform is just you embed your field element into a ring element. So that means you do nothing. Okay, so it's fast. And the reverse transform, you actually need to XOR all the elements, okay, the last part of your ring element into the other field elements. So, and the other transform parity is the opposite. So the first, when you go from the field to the ring, you just had a parity bit, actually. And the reverse transform is just removing this bit, okay? So can you go back to the other slide, the next slide? Yes, this one. So depending on how many packets you have and you want to generate, you will use the embedding of the parity, but they are very fast. And they are described in the paper. If you want, I can send you. If you
Yeah, I mean, it reminds me a little bit of some work some people did on something called optimal prime fields, where they also need to do a mapping before and after the encoding. I was just wondering if it was included, because I know this ISAL implementation also, that they are also really fast, right?
Yes.
So
I agree.
So it's impressive that you're managing to outperform them by that much.
Okay. Thank you.
Yeah. It looks magic. Thank you. We are running a little bit late, 3 minutes late, so I will ask you a question later on.
Okay.
Okay, thank you, Jonathan. So I forgot to introduce, we moved to the second part of this afternoon's session on end-to-end, on coding techniques. So that was for the implementation part. Now I will have a presentation on, well, sliding codes, why should we use them and when? And then we will continue with the presentation on quick and FEC codes and some experiment that could be done in this domain, so for the future works. So I will move to the pink box. Okay, so this is a presentation that I made in part at previous meeting at TSVW working group, but with new results and new stuff. So it's different. First of all, I would like to say that we didn't try to patent anything. Because it will experience different loss model. And then you do FEC decoding, you will construct the flow, and your goal is to achieve a specific target quality. So that's one of the key criteria. Each receiver must achieve a certain target quality. So you have several parameters, this loss model that will differ from between the various receivers. You also have this very important parameter, which is the latency budget, the FEC latency budget that you can afford for FEC operations and coding, decoding. If a lost packet cannot be recovered within this latency budget, then it will be lost forever. This latency budget does not consider any other source of latency. So propagation time, for instance, is not inside, it is out of scope. And then, of course, we want to compare several FEC codes. So the intuition, very basic intuition, with block codes, you are constrained by this block creation time. So if we have an isolated packet loss, then it can take time to recover from this packet loss. With sliding window codes, with this continuously sliding encoding window that slides over the data sets, then you have more opportunities to repair lost packets more rapidly. So that's the key idea, the key intuition. Now the question is, does it work or not with other types of packet losses? So once again, what can we expect from the use of sliding window codes? Well, we can expect lower FEC-related latency for the reason that I just mentioned. But we can also expect, and this is still on intuition, improved robustness. Why? Well, for two reasons, essentially. Because the sliding window will overlap with one another, so it will potentially be a good asset in case of long packet losses bursts. So that's one of the reasons. And the other reason is a consequence of the first one. If you have less latency with this scheme, then you can potentially accommodate larger encoding, decoding windows. So once again, you will gain from this point of view. So this is a few more words about the experimental setup. So we compared the RLC, which is this sliding window that we are proposing to TSVW working group. Very basic one, very basic solution. Nothing new inside. And we compare it with Reed-Solomon codes, that are ideal codes with small blocks at least, but those are ideal block codes. And we also included Raptor code comparison. Raptor code comparisons, unlike Reed-Solomon, are far from ideal, especially when you are considering small blocks, which is the case here. So you need to set up a few tricks. You need to artificially divide packets into sub-packets or symbols into sub-symbols in order to artificially increase the number of symbols per block, so going to larger blocks. So it's a trick, it's tricky. It is described in the RFC describing Raptor, but you have to do that. So the experimental setup is similar to what I presented just before. So you have this CBR transmission channel, which makes sense for the use case that we are considering. With 3GPP, we are considering constant bitrate transmissions. So in this case, you have 100 packets per second, constant bitrate transmissions. You have this target quality. We don't want to have more than 10 to the power minus 3 packets missing after FEC decoding, so that's target quality. We have this loss model, which is also a very important parameter, and then we have this latency budget, the amount of time you can afford to doing encoding, decoding operations. And in that case, we consider two values, a quarter of a second and half a second. And then we want to measure in the first step how much repair traffic we need to achieve this given target quality, 10 to the power minus 3 after FEC decoding. Given the loss model, given the loss model, given the target, the FEC latency budget. So what is the additional repair traffic you need to inject? And when you inject that repair traffic, of course, you will reduce the source application traffic very mechanically. I don't have time to go too much into details, but the way it's implemented must be considered. Especially with block codes, because depending on whether you have a single output queue at the FEC encoder or two queues, it will differ in practice. So just a few words about it. Let's consider block codes. If you have a single output queue at the FEC encoder, it means that you put in that queue all the source packets as they arrive in this queue. And then when you do FEC encoding, you put all those repair packets inside this queue. And then once again, you will continue to enqueue source packets. So since you are considering constant bitrate transmissions, it means that the traffic shaper that is behind this queue will have to will generate a lot of will generate a burst of, not a burst, but will send a sequence of repair packets followed by source packets, and then repair packets followed once again by source packets. And some source packets will be delayed because of that. So if you have a single output queue, it will be that will be the result. If you have two queues, one for source packets, one for repair packets, then the traffic shaper will serve alternatively one flow, one queue, and then the other one, and you will have this mixed transmission, source repair, source repair, source repair in that case. So that's important to take into account. We also focusing on 3GPP use cases, which means that mobility needs to be taken into account, and 3GPP has produced loss models for taking into account mobility. So typically, basically, you have two types of receiver. One is passenger of a vehicle, and the other one is pedestrian. If you are considering a pedestrian, this pedestrian will remain be an obstacle for quite a long time because it doesn't work for so fast. So it ends up in having two different, completely different types of loss models. As you can see in this figure, on the top, you have this vehicle passenger with where you will see isolated packet losses, more or less. And in the second case, you will have those long bursts of packet losses. So this is also something interesting, taking into account the official loss models. I will go directly to this slide. So this slide represents the amount of repair traffic you need in order to achieve the target quality 10 plus minus 3, depending on the mobility scenario, depending on the loss model you are considering, and for the various codes. So the y-axis represents this required repair traffic overhead. So the lower, the better, of course. And if you look carefully, you will see that, sliding window codes are always much better, significantly better than the other block codes, even Reed-Solomon block codes. Raptor are well behind all of that. So that's the main achievement. So it really makes sense. Then if you look more carefully, you will see that some of these scenarios cannot be addressed in a reasonable way with a reasonable amount of repair packets. This is the case for the worst scenarios. Here, for instance, for the pedestrian use case, having several hundreds of additional repair traffic is not reasonable. So, since we are considering a single source, a single data flow, you need to make a choice. Now that you have the results, you can make this choice. You need to choose the target code rate, the amount of repair traffic you can accommodate. This is one way to say that. The other way is to select the channels that you want to support. So both questions are more or less equivalent. And then from this, you can measure the actual latency that you can experience at a receiver. So very quickly, I don't have so much time left. Those figures are for the final situation. You have a single data flow with a specific latency budget, half a second in that case, with a specific amount of repair traffic, 50%, so code rate 2/3, sorry, in that case. And then you measure the experience latency at a receiver with this flow, depending on the scenario, mobility scenario. And what you can see is that with RLC, very good receivers, the one on the left curve, for instance, 1%, 5%, those good receivers will experience a very low latency, even if it is dimensioned so as to accommodate up to 480 milliseconds at most. So that's a good point, and Reed-Solomon will not succeed, does not compare so well in that case. Yes, it is fast. This is the next question. We do not implement our codes the way Jonathan did. So this is far from being the fastest FEC codes you can imagine, codecs you can imagine, but still it's significantly faster than Raptor codes, for instance, and more or less the same as with Reed-Solomon codes. So to conclude, yes, it makes sense to use sliding window codes. We experimented with those RLC codes, very simple codes, but you can imagine other types of sliding window codes. It will be more or less the same results. We focused on multicast broadcast communications, but you can have same or similar benefits with unicast communications as well. So that's all. I'm open to questions. Yep.
Stanislav Akamai, did you use Raptor RQ or Raptor?
No, we use the Raptor that are in the standard. So those Raptor are, well, those are the old Raptor solution. Okay. Raptor Q are not in the standard.
Okay. But performance could be better with Raptor.
Performance could be better in terms of, well, compared to Raptor, but still there will be more or less, well, there will be more or less similar to that of Reed-Solomon, just behind Reed-Solomon perhaps, or almost the same. But the idea of comparing with Reed-Solomon code and individual code is really to have the best solution possible with block codes in that case. I did not have time to mention, but the block codes typically are around 10, 20, less than 10 packets per block. So, oh, I see. Yeah, Marie-Josée.
So I have two questions. One is those codes are obviously based on convolutional codes that were done at the physical layer. So do they have the same capabilities or the same features? So your decoding, for example, is it based on a convolutional decoder?
No, we have sliding window codes. So I know you don't like convolutional terms, so I get rid of this adjective in our document, in our presentation. So what we're doing is just solving this linear system in the traditional way. No different.
Okay. And the other question is, again, going back to the word that we're not supposed to use, convolutional codes, have you thought of like other types of convolutional codes, the ones that you puncture, the ones that, you know, like the punctured codes that you can actually use to have different rates from the same code or things like that, or is just right now just a sliding window?
We consider the most simplest solution. So no puncture, nothing specific. Well, exactly the RLC codes that we are considering are exactly the ones that we specified in the associated internet draft.
Okay, no, it's fine. I just was wondering where your research was.
Yeah.
Okay, thank you.
You're welcome. Oh, yes.
Hello?
Yeah.
Yes. Okay, good. I'm on. Thanks, Vincent. This is great. Very interesting. I think we need more of this, you know, research results and discussions. Clearly very useful for lessons learned and moving on with research. So just a quick, very quick question on this comparison. Obviously, you know, with FEC, you have a fixed coding scheme with a fixed coding rate, meaning the amount of redundancy is fixed. But with RLC, I'm not sure. I mean, different protocols have different ways of, was it dynamic, adapting to the loss of the channel or not? Or I'm trying to see how you can actually have some comparison between the different adaptation or lack of mechanisms inside each of the protocols. Obviously, the Raptor codes are rateless, so they keep sending until you get it. Right.
Yeah, we are not considering adaptation dynamic aspects here in this case, for sure. This is a multicast broadcast scenario, so you have a single flow. and you have to decide in advance what we want to use in terms of code parameters. So there is no possibility to adjust it. Well, we are not considering dynamic adjustment of those parameters, code rate, for instance, during the session. It does not make any problem to change it if you have unicast communications and feedback flow that will tell you what is the network situation, network conditions. If you have that, you can do that very easily with RLC codes, with those kinds of FEC codes. Nothing is fixed in advance. You need a new repair, you generate it, you send it. You don't need it, you don't repair, you don't generate it, and that's all. So all of this are side questions that are not considered in this work, where we essentially and only wanted to compare block versus sliding window codes. But yes, in practice, if you have unicast communications, as in Tetris, we can do that. But
right. This is good. So that's good that you confirm that it was indeed the same scheme of fixed coding rate. So that means it's indeed apples to apples. This is good.
We are running late. I'm sorry. We are 10 minutes late. Okay. So I prefer to give the floor to Jan immediately. Thank you.
All right. Can you hear me? Okay. My name is Ian Sweat. I'm going to talk about Quick FEC. I want to call out one thing about, actually, how many of you are familiar with the Quick effort at IETF? Okay. Oh, okay. So enough that I won't go into it too much, but Quick is a transport built on top of UDP. It's designed to be encrypted always. Because it's built on top of UDP and not TCP, the opportunity for FEC is more promising than most TCP-based transports. And I think that probably is sufficient for what's in the slides. We did a V1 of FEC. It was in the original design. We tried experimenting with it in various ways, but the core foundation was it had a single XOR recovery packet. So you would have a block of a certain size, and every once in a while you would rotate blocks, and you would either spit out an XOR recovery packet at the end of the block or not. Those are basically the two ways you could do it. So, and you could end a block prematurely. So if for some reason, you entered quiescence and you didn't have anything to send, you could just end a block and have an XOR that only covered, say, 2 packets instead of 10, if that's what you wanted to have. So it's built into the transport as a core feature. It was in the core framing, and yeah, it recovered at a packet level. So it wasn't. It was kind of outside the crypto envelope. So the main issue with it is packet loss on the internet, at least in our use cases for unidirectional unicast traffic, actually is highly correlated. So 70% of our FEC packets, even when there were losses to repair, did nothing because we had no way of generating more FEC in our scheme, and there was no way to resend the exact same quick packet to repair enough holes that then the FEC packet could be used. Because in Quick, the packet sequence number is actually also used as the initialization vector in the crypto. And so it always must continually increase because if you reuse the initialization vector in crypto, everyone becomes very sad and you leak your key. So anyway, so this particular flaw turned out to be a sufficiently large problem that it actually turned out to be, for HTTP traffic, better to just send a random packet, like what we do in tail loss probe for TCP, than it was to send an FEC packet, because so often the thing you sent was just useless. Yeah, and the fact that it was integrated in the core transport really caused a lot of programming headache. I mean, I think we probably spent close to 2 developer years trying to make it work with different experiments. So we ran experiments where we just ran it at a fixed rate. We ran it at a rate that was half of the congestion window, under the theory that you would never want to bother with FEC and wait an entire extra RTT. And we ran one which basically just replaced a aggressive tail loss probe with a forward error correction packet. And in all cases, it was just strictly negative, or it turned out to be, it was slightly positive in a few cases, but in the cases it was positive, you could just send any random packet that hadn't been acknowledged and it was equally good. So that was kind of a bummer. But now we know, we learned a lot. Next slide. So this turned out to be we found this out after we ran all these FEC experiments. We should have gathered this data first. So we gathered a bunch of data early on that was what quick packet loss would have looked like on the internet if we weren't actually sending any data. And it turns out that's not super representative of like what it looks like when you're actually running a transport over the internet. So when we weren't sending any data, like it did kind of look like IID approximately. It wasn't too far off. But when you're actually using the network, at least to some extent, you know, whether it be search or otherwise, this is the CDF you end up with. So you can see that about 30% of the time, the packet loss distribution, I should say, this is within an RTT. So this is, if you're familiar with TCP, the concept of a loss epoch, like when you go into recovery. So this is how many packets were lost from the first packet that was lost to an RTT later. So it's not true burst size, but commonly these did actually arrive in bursts all the time. And especially since we're considering approximately half an RTT as our, a coding length or a window length, then these really started to play in. So around 45% were in 2 packets, and there's still quite a bit of energy at the tail up around 8. So maybe like by the time you get to 8 packets lost in a single RTT, you're, what is that, around 90%? So it's fairly correlated. So I guess 1 is the most popular number, but it turned out 2 was like almost as popular. So next. So the current things that we've been thinking about is, we learned from the first time, okay, this tail loss probe thing should work. It should be possible to send a packet and have it be useful no matter what. And if it's an FEC packet and there was only 1 outstanding packet, it would immediately recover. And if that wasn't sufficient, we would at least A, learn something, because it would generate an acknowledgement that would cause us to know what to send. And B, we wouldn't have wasted that packet. So it should be still possible to use possibly something like a sliding window code to only generate a packet at the tail when you enter quiescence for web applications. That should still be a valuable concept. We haven't done the work to do it, but yeah, it potentially could be useful for other applications that are sensitive to tail latency. Real-time communications like RTP for WebRTC seem like an obvious use case. We've started to look into doing WebRTC on top of Quick. WebRTC, I think currently the most advanced scheme that is standardized or semi-standardized is a matrix of XOR forward error correction packets is the last draft called Flex FEC. Apparently it works reasonably well, but I haven't really evaluated, but it kind of uses this matrix to deal with the fact that losses are sometimes correlated. So you can kind of, as long as you don't lose 2 packets in the same row or column, like you're okay, essentially. And one thing about particularly WebRTC and all of this, we really need something that's fast enough that especially the decode can happen on a relatively constrained device, i.e. a phone. I mean, it doesn't have to be the world's oldest phone, but if you can't run it on an iPhone, then in practice, that's probably not going to be widely acceptable because a huge portion of our traffic is from iPhone and Android. And then the last idea is a quick tunnel. So this kind of goes on what Marie was talking about. In Quick, you can't actually terminate the transport without terminating crypto, which is great on a variety of levels, but it means something like a performance-enhancing proxy is like literally impossible on the transport layer. But there might be a possibility of using FEC tunnels as a replacement for a performance-enhancing proxy in cases when you know that some sub-portion of a network has available bandwidth that you can use. So it doesn't have to be end-to-end. It could be a tunnel in the middle that's in a provider's network, maybe from where they normally would install a performance-enhancing proxy to the wireless head end or something. I don't know. So any of these use cases sound potentially interesting. And we have some active development in the latter 2 for like applications. And the first, obviously, HTTP, where Quick is around 7% of the internet right now, so that's like a thing. So that there's a lot of deployment there. So any help from this group in advising or suggesting experiments that should be run, or the willingness to run experiments, because all of the code is open, would be welcome.
Yeah, thank you. We have 10 minutes left, so time to take questions. Yes.
Morten Petersen. So on the performance thing, I think you will find no issues. So there's been a lot of work in the last couple of years, and also with this new stuff, it's that has not been a problem for a long time. Running even on sensor nodes, so you can get really reasonable performance with the coding. I know some people that are looking at Quick and looking at how to put in, for example, a sliding window code. What would be, in your opinion, the starting point? Because there are multiple implementations. For example, the Go one, and there's the one that is now sort of been lifted out of Chromium, I think.
Yeah.
And so I wonder if you have some advice there where you could point people to say, this is a good place to look.
It depends on what you're attempting to accomplish. I think if you're attempting to accomplish an experiment involving FEC to show its end-to-end viability and maybe its performance in like a controlled environment, I think probably the Go implementation is actually the easiest to iterate on, because it's Go. Assuming you're familiar with Go, it seems like they were able to write their implementation with a lot less time, like developer time, than we were. The Chromium one is like almost identical to what we run internally. So I mean, it's but it's all C++. It's quite well optimized. It's not 100%. I mean, it still has work to do, but it's fairly fast. So if you're looking for something that's going to be a more production, like give you realistic performance numbers, I think the Chromium one is what I would recommend. And you can either pull that directly from the tree, or there's something called ProtoQuick. There's also something called LibQuick, but that is, I think, now about a year behind, so I wouldn't grab that. It probably will not be interoperable with any of our servers, or at least not for long. And so it's just, and we're trying to move to the IETF specification of Quick as quickly as we can. So hopefully they'll be almost compatible or completely compatible. But yeah, so it depends on your use, I think.
But for sure, there are common interests between Quick, you, and this research group. Yeah. So I would suggest to follow up, to continue this discussion, and to see how can actual progress on this question, which is very important to all of us. I see there is a question for Emmanuel or Nicolas. Yes, you have the floor.
Yes. Just a quick question. We did not really understood the CDF drawing. Just wondering, what is the size of the Quick window? So because it means there that 80% of the time you just have only 4 packet losses within a window?
Yes, so this is essentially packet losses per window. So yeah, I mean, the window might be different. So in some cases, the window might be 10 packets.
This is not, okay, it can be different size of a window, so, okay.
Yeah, this is more of a TCP loss recovery, like epoch concept. So it's not necessarily what you're used to in a forward error correction metric, but like it makes sense for kind of loss recovery congestion control metrics.
Okay.
But within what kind of test was it? Like, was it in a internal network testing or in control environment, or?
No, this is across. It's either all Chrome. I think this is across all Chrome and YouTube. Chrome to YouTube and Google traffic across 1 week in like June of last year, for probably like millions of connections. So this is public traffic coming out of Google and /YouTube.
Okay, I suggest stopping questions here because we are just on time. If we skip the last part. Thank you very much. So I see many opportunities for continuing this activity on FEC and how to apply it to other protocols within IETF. And yeah, it's very important for us, for IETF in general. I think Alison will agree. So let's continue on this topic and the list, and let's continue just after the meeting. We can take advantage of being all together to discuss this. So thank you everybody for this meeting. I would like to do special thanks to Marie-Josée. Thank you, Marie, for your help. Okay, see you next time. Bye. Everybody signed blue sheets? No?
Yeah, we decided we essentially. Yeah, I mean, it was adding code to one setting that, it was a new around a year ago,